All right, so now we have serine proteases. So this is a class of enzymes, serine proteases, that's plural because there's many enzymes that all perform the same catalytic function, which is to cleave a polypeptide bond. How they're all different is the specificity of the residue that's adjacent to that bond to be cleaved. So we're going to learn about 3 serine proteases. One of them is called chymotrypsin. That's going to have an R group like tryptophan, tyrosine, or phenylalanine, so bulky aromatic side chains. We're going to have something like trypsin that's going to cleave when this is a lysine or an arginine residue, so a long sort of chain that terminates in a positive charge. Or elastase, that's an enzyme that recognizes small nonpolar amino acid side chains like glycine or valine or alanine. Nonetheless, they all perform the same catalytic function. They are called serine proteases because of a catalytically active and important serine residue that's in the enzyme active site. That serine residue is actually part of a series of 3 amino acids that comprise what's called the catalytic triad. I'm not going to spend too much time talking about aspartic acid because aspartic acid basically just serves as an electrostatic catalyst. It is going to help by donating electron density to histidine 57 because histidine 57 initially is going to start out by acting as a base. So its basicity can be enhanced by aspartic acid. Again, histidine 57 is going to act as a base, and we're going to see early on it's going to act as a base to deprotonate serine 195. The catalytic role for this serine is it's going to act as a covalent catalyst. So we'll see that all play out here in just a minute. The last little piece here to highlight is something that's called the oxyanion hole. So like the name implies, it's a little hole, it's a little pocket in our enzyme active site that's going to help stabilize a negatively charged oxygen that is developing when we do this chemistry. So there's some backbone atoms here that are going to allow us to hydrogen bond to this negatively charged oxygen that develops as we form a tetrahedral intermediate. So that's all of our pieces that we have here. Remember, we're always doing 3 steps in our enzymatic chemistry. We need to do chemistry on the substrate. We need to use all of our reagents, which generally means the incorporation of water, and we need to regenerate the enzyme active site. And usually water is what's used to sort of complete that process. Okay, so here we've got our substrate polypeptide. Again, we've got an N-terminal portion and a C-terminal portion and the peptide bond that's going to be cleaved. So again, this peptide bond really is this oxygen and then that nitrogen. So those are the atoms that are connected there. So how this starts is we're going to have serine acting as a nucleophile, but its nucleophilicity is going to be enhanced by histidine 57 acting as a general base, remembering that its basicity is enhanced by aspartic acid. I'm not going to talk too much more about that catalytic triad, but histidine 57 acting as a general base serves to deprotonate serine 195, allowing it to act as a nucleophile. It's going to nucleophilically attack this carbonyl carbon, and we are going to generate a tetrahedral intermediate. So let's get to our first tetrahedral intermediate here. So here's our first tetrahedral intermediate. We have not broken this peptide bond yet, so that peptide bond is still intact. Here's the tetrahedral intermediate, okay? This serine is connected here, so we're gonna try to show this as best we can. This serine is this serine here. So we've covalently connected this serine to the rest of our peptide. Now, this atom here, when we had our peptide bond as a carbonyl, was sp2 hybridized and it was trigonal planar. When we form our tetrahedral intermediate, we change this to an sp3 hybridized carbon atom. It's tetrahedral, so it changes its shape, and it has this oxygen atom that's negatively charged. So again, this oxyanion hole is available to help stabilize that negatively charged oxygen that we generate in our tetrahedral intermediate. So let's put all of our pieces here together, take stock of sort of what we have. Histidine is not in its correct protonation state. Serine is now connected to this tetrahedral intermediate. We have yet to cleave our peptide bond, and we're utilizing this oxyanion hole to stabilize this tetrahedral intermediate. think back to a lot of your uncatalyzed reaction mechanisms. We'd form a tetrahedral intermediate, then we decompose the tetrahedral intermediate. So we are going to decompose this tetrahedral intermediate by reforming this pi bond that allows us to regenerate this carbon atom as an sp2 hybridized carbon atom. So we sort of change the shape here. We're going to come out of that oxyanion hole. But when we reform this pi bond, we can't have 5 bonds to carbon here, so something needs to break. We could break this bond right here and just release serine, but that's just going to take us back to the beginning. That's not going to be helpful. What we want to do in this chemistry is we want to break this peptide bond, right? Breaking bonds is going to be facilitated by making leaving groups better leaving groups. We're going to do that by protonating them. So here again is a role for histidine. Histidine 57 now is going to act as a general acid, and it's going to protonate the nitrogen of this C-terminal peptide, facilitating the cleavage of this peptide bond and sort of completion of this chemistry here. Okay, so now let's take stock of what we have. We've cleaved our peptide bond, so we've done that first step. So this can now diffuse out of the enzyme active site. So let's finish this out here. Decomposition of this tetrahedral intermediate and breaking this peptide bond is going to get us now to this intermediate. We call this an acyl-enzyme intermediate. We've regenerated this sp2 hybridized carbon, which means we're not involving the oxyanion hole, but we are still covalently connected to the serine. Okay, so our enzyme active site is not regenerated, right? We've got histidine 57 in its right protonation state, but our enzyme is still attached to the N-terminal portion of this polypeptide. Okay, now like we see with so many of our enzymes, water is going to be able to diffuse into the enzyme active site, and it's going to complete the regeneration of all of these amino acid side chains. Okay, we're going to have histidine 57 acting as a general base, deprotonating water, and that's going to increase its nucleophilicity towards attack on this carbonyl carbon of the acyl-enzyme intermediate. So again, formation of a tetrahedral intermediate here. So let's go ahead and find that tetrahedral intermediate here. So here is that hydroxyl that just kind of came in here. We form this tetrahedral intermediate. We change the hybridization of this carbon atom, so it's now sp3, and we dip back into the oxyanion hole to get stabilized. So our tetrahedral intermediate, now this is our second tetrahedral intermediate, using this oxyanion hole again to be stabilized, but we still are not back because this guy is not in its proper protonation state, and serine is still connected here to our N-terminal peptide. So anytime we form tetrahedral intermediates, often the next step is we're going to decompose those tetrahedral intermediates. This is the bond now that we'd like to break. It's going to break more easily. This will be a better leaving group if we can protonate it. So histidine 57, now acting as a general acid, is going to protonate the oxygen of our serine residue, okay? And if we get to our very last piece here, okay, we are going to protonate serine there, okay? And then our N-terminal peptide, let's put this hydroxide right here, that's where it's supposed to be. That N-terminal peptide is now cleaved away from our serine. Our serine is back in its proper sort of free state, and our N-terminal peptide can now diffuse out of the enzyme active site. So looking back at all of these important residues, serine is back in its protonated and free state. Histidine 57 is back in its deprotonated state. Aspartic acid never really changed its state. It's still just doing its chemistry as part of the catalytic triad. And the oxyanion hole is just kind of living there to help us stabilize negatively charged oxygen atoms that develop when we had our tetrahedral intermediate.